Well, Professor Clements here with you doing an example in electrostatics, chapter 18, if you're using the OpenStax College physics textbook. We consider two charges on the x-axis, minus 3 nanocoulombs at 3 centimeters, 2 nanocoulombs at 20 centimeters. Where could we put a third charge such that this third charge would have zero net force on that charge? So we'll be doing a calculation here. The first thing we should do is think about where is it possible that the net force would be zero. If we consider to the left of the minus 3 nanocoulomb charge, we cannot have net force zero there because the larger charge will be closer to doing the calculation of k, q1, q2 over r squared. We have a large q, we have a small r, we'll get a large force. So we can't have a balance of forces there. In between the two charges, if I put a positive charge, say at the 10 centimeter mark, it would be attracted to the left to the minus 3 nanocoulomb charge. It would be repelled by the 2 nanocoulomb charge. Two forces to the left, no force to the right. Those cannot add to zero. Off in the region to the right of the 2 nanocoulomb charge, we can have a balance of forces. We're closer to the smaller charge, the forces can add up to zero. So that's the analysis that you should undertake in a problem like this. Before you write down any equations, consider which region could the forces add to zero. And now the equations. We're going to let x be the position of this charge. And we know x will be bigger than 20 centimeters. That'll help us when we write down our solution. We're going to add the forces from the two charges. So the minus 3 nanocoulomb charge, x is the position where charge q is located. The minus 3 is the location of the minus 3 nanocoulomb charge. So there's our r, and we have to square it. The 2 nanocoulomb charge is located at 20 centimeters. X is where our charge q is located. You can observe here the k's cancel, the nanocoulombs cancel, the q's cancel, and that simplifies our expression to minus 3 over x minus 3 squared plus 2 over x minus 20 squared. If I multiply by the two denominators, I'll end up with minus 3 times x minus 20 squared, 2 times x minus 3 squared. I square the parentheses. You can see that has happened on the next line. And now we distribute the minus 3 and we distribute the plus 2. And you can pause this if you want to inspect it. And now gather like terms. I have minus x squared plus 108x minus 1182. And I prefer a positive in front of the x squared, so I just reversed all the signs. X squared minus 108x plus 1182. Quadratic formula can be applied here. So minus b plus or minus square root of b squared minus 4ac over 2a. The a is a 1, the b is minus 108, the c is 1182. So substituting those in, we see this expression. Again, pause if you want to verify that. And in doing the calculation, you see I had to repeat the calculation. I changed that to a 2 instead of being a 4. But doing the discriminant under here, b squared minus 4ac, and then taking a square root, that produces 83.28. One time I have to add it to 108. The second calculation is subtracted from 108. This produces two results. When I subtract, I get 12.4. When I add the 83.28, I get 95.6. And of course this is the one that's greater than 20 centimeters. That's in the solution region. And that's the location where the force would be zero. If you want to verify this, you could take these numbers and substitute them back into here, and you'll find that you do have zero, aside from these are approximate numbers, but it'll be close to zero. That's how you solve the location where the net force is zero when there are two charges present. It'll reduce to a quadratic formula calculation. So keep practicing.